Greetings to all. So today in this video, we are going to discuss about optical sources and detectors in the subject optical communication. So first let us consider this of third unit. So this is about optical sources and detectors. First of which deals with optical sources and second of which deals with the detectors. In this video, we are going to discuss what is photodetector, what are the types of photodetectors, what is the purpose and the working principle of photodetector in this video. So let us start with the diagram, that is the block diagram of optical detector. This is our block diagram of optical receiver actually. So actually this is a digital optical receiver which will consist of a photo detector as in first block and followed by preamplifier, equalizer and then filter. So this overall block diagram which is called as optical receiver. And we know that and where we are using that photo detector and what is the purpose of photo detector. So as we know the photo detectors that can be connected or that can be used in the optical receiver, that is at the receiver side. The purpose is that the input of this optical detector is nothing but, that is photo detector is nothing but optical signal, or we can call it as light signal. So that light signal that has to be converted into the equivalent electrical signal. So that is the purpose of photo detector. And that signal what we receive from this photo detector, that has to be amplified, and so that we'll be using that preamplifier and then which is given to the equalizer just to balance the, that is to just to equalize the signal from the preamplifier circuit. Finally we'll be using that filter just to avoid the noise or to filter out the noise signal, and finally which will be given to the destination. There we can just get the detector electrical signal as that of the actual original signal which is given to the transmitter side. So basically what is photo detector is nothing but, we can say that basically it is a transducer, because one that is one form of energy is converted into the another. So that is why it is basically, it is also called as transducer. And here the conversion is that which converts the optical signal into electrical signal. So we can call it as opto-electrical converter. So this is also called as opto-electrical converter. So this photodetector which receives the transmitter optical pulses by means of optical fiber, and that optical signal which may be in voice signal or it may be in video or it may be in computer data. Okay, so that will be converted into an electrical signal. What you are getting that signal from that photodetector is its very lower value, so that will be amplified by means of preamplifier circuit. So that is the purpose of preamplifier in the optical receiver. Following to this one, and first we can just discuss about what are the types of photodetectors. Okay, and before going into the types of photodetector, let me explain what is the basic principle which will be used in the photodetector. So this photodetectors which will work on the principle that internal photoelectric effect, which means the photons of the incident optical signal which has the energy and which is either equal or larger than that of energy band gap value of the semiconductor material used. So that signal, that optical signal, that can be get absorbed. So only when this band, that is band gap energy value is greater than that of or equal to that the energy level, only then that optical signal is get absorbed by the material. So this results in excitation of electrons from the valency band to the conduction band, as we know. So which will create the electron volt pairs. Okay, so this electron volt pairs, which is, since it is thermally generated, so we can call it as photo-generated carriers. So this excess carriers on and above the existing thermally generated carriers, we can call it as photo-generated carriers. Why? Because which is mainly it is only generated only by means of photon of energy. So this photo generated carriers, ultimately what will happen, and there is an external circuit and there will be a flow of current, that is called as photocurrent. So due to this photo generated carriers, there is a flow of current through the external circuit, that is called as photocurrent, or we can call it as photovoltage. Anyway, it's an electrical signal. Okay. So now the types of photodetectors. So basically based upon the structure, we can just call it as photodetectors into two categories. One is bulk, the other one is junction photodetectors. And then based upon the non-multiplying, that is the internal mechanisms for multiplying the photo-generated carriers within the highly doped region, we can just classify into two types. One is non-multiplying type, other one is multiplying type. So the best example for this non-multiplying type is nothing but pin photodetector. That is PIN, pin photodetector. Or we can call it as PN junction photodiode. So this is one of the type of non-multiplying type. The multiplying type photodetector is avalanche photodiode. Why? Because there is a multiplication of photocurrent within that is highly doped region. So that it is called as multiplying type. And then depending upon the energy which is absorbed by there is a energy of there is photon of energy which is absorbed by the material. We can just classify these photodetectors into intrinsic and extrinsic category. So with that, as the name implies, intrinsic is nothing but pure form and extrinsic is nothing but impure form. So in case intrinsic photodetectors, and there will be that is photo-generated electrons and holes pairs which are created by the direct transition, which means direct transition of electrons from valency band to the conduction band. So we can call it as band to band transition. And but in the case of extrinsic photodetectors, these photons excite electrons from the deep level traps to conduction band or from valency band to the deep impurity. So in most of the application, we'll be using that intrinsic photodetector. Why? Because, and in case of extrinsic, due to that efficient absorption of photons and fast response speed, we'll be using that intrinsic photodetectors when compared to the extrinsic. So as I told you, the extrinsic is nothing but it's an impure form, which means there is no efficient absorption of the photon of energy by the material. Why? Because it's an impure, and we can say that the response speed also it's very slow. So that is why in most of the application we'll be using the intrinsic photodetectors. And then these photodetectors are often classified as an homojunction or heterojunction based upon the whether the same material is used or the different materials are used for P and N type. So suppose if the both P and N type materials are the same material, then we can call it as homojunction. Suppose if it is from the different materials, then we can call it as heterojunction photodetectors. So this is about the classification of photodetectors. So first and foremost, we'll be just classifying into non-multiplying and multiplying type. Second is based upon the whether the same material or different material used, then we can call it as homojunction or heterojunction. And then based upon the purity of the material used, we can just classify into intrinsic and extrinsic photodetectors. So this is about principle of photo generation. So in this intrinsic photodetector, the minimum energy of the photons corresponding to the frequency or wavelength of the photons that would be absorbed by the semiconducting material constituting the photodetector. So that depends upon the band gap value of the material as we discussed in your previous slide. And this is a formula. Here we can just find out what is the longest wavelength which corresponds to the shortest frequency, or we can call it as lowest energy photons. So that can be observed by the semiconducting material, that can be calculated as HV minimum is equal to Eg. From this we can able to find out the what is the longest wavelength for that particular material, semiconductor material used. Lambda maximum is 1.24 by energy band gap value of the semiconductor material in terms of electron volt, and the unit for this lambda maximum is micrometer. So this is the formula where we can just find out the. And next one is characteristics of a general photodetector. Either it may be a pin photodetector or it may be an avalanche photodetector. So these are all the characteristics. So first is nothing but size compatibility, which means the size of the detector, it must be compatible with the size of the fiber carrying the light signal. That is, which means the radius of the core. Why? Because we are going to connect that optical fiber to the photodetector. So obviously it should be compatible with the radius of the core. Next is nothing but high conversion efficiency, which means the photodetector must be able to produce maximum electrical signal for a given amount of received optical signal. So that conversion efficiency should be high. Third is nothing but high sensitivity at operating wavelength, which means the photodetectors are based upon the suitable semiconductor material. Why? Because based upon that energy band gap only, the maximum amount of photon of energy that can be get absorbed. So this is also one of the characteristics of any photodetector. And next is nothing but high response speed. So in terms of response speed, so detectors must be capable of converting fast changing optical signals which carrying millions of bits of information to the corresponding electrical signal. So which means the response speed should be high. At the same time, the response time should be as low as possible. Okay. So next one is minimum noise. So this photodetector, it should have extremely low noise. So there should not be any noise associated with the photodetector or any noise associated with the amplifier. So that noise signal should be as low as possible. So these are all the characteristics of any photodetector. And then as I told you, based upon the internal mechanism used, that is internal mechanism for multiplying the photo-generated carriers, and there are two types. One is non-multiplying, the other one is multiplying photodetector. So what we are going to discuss is non-multiplying type, which is nothing but pin photodetector. Here it comes pin photodetector structure. So this is actually an p-n junction. So p-type and n-type material. So in between there is a highly doped region which is sandwiched between p and n-type material. And this p-type is, that is a p-type material is connected to the negative bias voltage, and n-type is given to the positive bias voltage. So which means reverse bias voltage is given to the circuit. And at the same time the photon of energy HV, which can be incident on the highly doped region. In here this region we can call it as intrinsic region, or we can call it as highly doped region. So once it is given to the reverse bias voltage, and when this light signal, which is nothing but photon of energy HV, which is incident on the highly doped region, what will happen is there is a recombination of 4 electron volt pairs are generated within this region. So this region, which is also called as depletion region. So due to this electron volt pairs combination within this depletion region, we can call it as photo generated carriers. So that pairing of electron and volts, we can call it as photo generated carriers. Why? Because only because of this photon of energy HV, the electron volt pairs are created. So that we can call it as photo generated carriers. So due to this photo generated carriers, again which will move towards the positive and negative terminal. So movement of this photo generated carriers, and there will be a flow of current in the external circuit. So that current is called as photocurrent. Okay. So first one is photo generated carriers within the highly doped region. Due to this photon of energy HV, once it is incident on the highly doped region, there will be a creation of electron volt pairs. So that thing we can call it as photo generated carriers. So movement of this photo generated carriers, there is a flow of current in the external circuit. So that is called as photocurrent. Okay. And again there will be minority carriers within that depletion region, and that will move towards the negative terminal, that is holes that can move towards the negative terminal, and electrons that can move towards the positive terminal. So due to this movement, there will be an increase in the diffusion length. So diffusion length is nothing but it is the length, or it is the distance taken by the hole to move towards the negative terminal, and it is time taken, or the distance taken by the electron to move towards the positive terminal. So that can be denoted as Ln and Lp. Ln is nothing but diffusion length for electron, and Lp is nothing but diffusion length for hole. And similar way, and there is a movement of minority carriers towards the positive and negative terminal. So the time taken by that the minority carrier, we can call it as carrier lifetime. Now by combining this diffusion length and carrier lifetime together, we can able to write the relationship between this lifetime as well as diffusion length for both holes and electrons. So this is a formula we can just use to find out the, or to relate the relationship between carrier lifetime and diffusion length. So next comes, this is the energy band diagram of pin photodiode. So the photons with energy greater than or equal to the band gap energy of the material that can generate free electron volt pairs that act as in photocarriers. So this is a region where there is a photo generated electrons and volts that is combined together, so that this region we can call it as active region. This is also called as depletion region. So movement of this photo generated carriers from hole, that is a photo generated holes from year to year, or photogenerated electrons from conduction band to the valency band, and there is a flow of current. So this photogenerated carriers which will create the current called photocurrent. So this this is possible only when this photon of energy HV, which is greater than that of energy band gap value of the semiconductor material, is possible. So this is about the energy band diagram photodiode. And next one is, as we discussed already, we can able to find out the upper cutoff wavelength. That's nothing but lambda c by using this formula, 1.24 by energy band gap value of the particular material used. And this energy band this cutoff wavelength is about 1 mm for silicon and 1.6 mm for germanium. For longer wavelength, the photon energy is not sufficient to excite an electron from the valency to the conduction band. So at the lower wavelength, and the photo response cuts off as a result of the very large values of as at the shorter wavelength. So only by means of that wavelength we can able to find out and what is the upper cutoff wavelength, and lambda c that can be determined by the band gap energy of the material. Next one is key parameters of pin photodetector. That is the characteristics of pin photodetectors that can be measured only by using two parameters. One is quantum efficiency, next one is responsivity. So what is that quantum efficiency is nothing but which will be that is represented in terms of percentage. And actually this is it ranges from it is theoretically speaking it is equal to 1, but practically speaking which is less than that of 1. So since as I told you which can be represented in intage, so if it is 0.99 then we can call it as 99%. So basically what is it, quantum efficiency is nothing but, and it is a ratio of number of electron volt pairs generated to the number of incident absorbed photon. That is output is nothing but electron volt pairs generated, and input is nothing but the photon of energy which is incident at the intrinsic region, or calculated as highly doped region. From this we can able to find out the quantum efficiency. So IP by Q by P in by HV. By using this formula we can able to find out the efficiency. So as I told you, it can be measured in terms of percentage. And this quantum efficiency of photodetector, it's generally expressed in terms of that is a percentage. And as I told you, which is less than that of unity. And next, responsivity. So this responsivity is also one of the important parameter that can be used to characterize the photodetector, and which is nothing but it's a ratio of photocurrent to the optical power. So again it is output by input. So as we know that photodetector, the output is nothing but photocurrent and input is nothing but the incident optical power. So by taking the ratio between these two, we can able to find out the responsivity. And this is the variation of responsivity of an ideal photodetector with the practical photodetector in terms of wavelength. So this is about the ideal one, and this is for the practical photodetector. In this graph, which shows the responsivity versus wavelength and of a photodetector based upon the material used. Suppose if the photodetectors are made up of silicon, then we'll be getting the responsivity in terms of 0.6, which is nothing but 60 percentage in terms of quantum efficiency. Suppose if the semiconductor material is by means of germanium, which is made up of germanium, then we will have the quantum efficiency in terms of 40%. And this, if the photodetectors are made up of indium gallium arsenide, then we may have that quantum efficiency that is above 90%. So this responsivity characteristics of photodetector is based upon the different materials used. So this is due to the fact that every material has a characteristics band of absorption. So only based upon that we can able to find out the responsivity of the particular material used. So thank you for your patient listening. Thank you one and all.